Okay, welcome back, everybody, to Real Analysis. For those of you who are watching online, this is lecture 21, and if you're wondering why it says 2011 instead of 2010, it's because the original taping we had some problems and weren't able to record the lecture. So this is being inserted in the stream of 2010 lectures. We're going to talk about continuous functions today. And if you recall from last time, we defined what it means for a function to be continuous. So loosely speaking, what does it mean? It means that a function is continuous if close enough points get mapped to close points. In other words, you have some function that is taking some space x into some space y, and we want to say it's continuous if it doesn't tear the space up in some funny way, right? You could imagine, for instance, having a function that looks something like this. So here's a function, and it takes some space, and maybe that's x, but maybe it maps the space to some other space. Like so, and you could imagine that, you could imagine this being the space y, and this would not be a continuous function. Why is that? Well, because morally speaking, there are close points here which get mapped far away in some sense, right? That's loosely speaking. To be a little more precise, we want to say this function is continuous at a point P if no matter how close you are in the codomain, you can find a ball in the domain that such that if you're within a ball from a point P, then the image is within that epsilon of the image of P. Okay. So in this picture, maybe I'd take this point, P, and I'd ask, is this function continuous at P? And we'd have to say no. Why is that? Well, we'd say no because if you take because there is an epsilon like this one. So here's an epsilon ball. Such that what? Well, such that if I look, sorry, this isn't P, this is F, excuse me. There's some P here. This is F of P. And the function is not continuous at P because if you look at its image and you draw a ball around it, for this particular ball, there is no delta ball around P that will map completely inside here. One way to see that is if you did take any ball around P, no matter how tiny it is, very, very tiny, you're going to end up getting some pieces of the image that live here in some sense, right? That's part of the issue, right? So this function's not continuous at that point P. Are you with me? Okay. Okay, great. So just to make this connection a little more integrated with some of the things that you've already seen, we also saw that there is a sequence version of the definition of continuity as well, which says the following. It says that for every convergent sequence in X, the limit of the images is the image of the limit. So in this picture, what that's saying is if the sequence is convergent, so let's pick a point here where we actually believe it's continuous. So how about this point here? Let's call this point T. Now, if I look at sequences that actually converge to T, let's call these points a bunch of points that converge to T, T sub n. is it the case that their images, whatever they are, here's f of t, here's their images, f of tn, do their images converge to f of t? And if the answer is yes, for all such sequences, the function is continuous at that point p. And it's continuous everywhere if this is true, no matter what sequence you're looking at in the domain. Okay? Okay, this is what we talked about last time. And so what I'd like to do today is to give you still a third characterization of what it means for a function to be continuous. This is one, the epsilon delta definition. This is probably the most familiar one that you might have seen perhaps in an advanced calculus course. This second one is a sequence definition. And so now there is, in fact, a third characterization, which is a topological characterization of continuity. It has to do with open sets. So this is, I think, one of the most useful, one very useful characterization of continuity. It says the following. Here's a theorem. A function from x to y is continuous if and only if the following is true. And now I'm going to give you a definition that has only to do with talking about open sets. So it's a topological characterization. I claim a function is continuous if and only if for every open set U in Y, the inverse image of U, F inverse of U, is open in X. Okay, so now I have to remind you, what does it mean to be an inverse image? Some of you will be familiar with this idea. This notation, f superscript minus 1, is supposed to mean the inverse function of f. It may not be a function, but it describes the inverse image of some set U. It's defined to be all points that get mapped into U. Okay, so it's a set of all points that get mapped into U. So a picture here is probably in order. Suppose I have some space x and a function, some space y. You might take a ball or some blob here. Here's some set U. Yes? So now, one question I could ask is, what is the inverse image of U? Well, it's the set of all points over here that get mapped into U. So let's see, maybe this point if this point gets mapped here, then its image is in U. So this point is in the inverse image. Now, this function may not be, its inverse may not exist. That is, this function may not be one-to-one, in which case it may be the case that several points get mapped to the same point. Are you with me? That could happen because the function is folding in some sense. Okay? That's still fine because this definition just says look at all the points that get mapped into U. Maybe there are pairs of points that get mapped here. And so, it's possible the inverse image could have pieces. Right? That's okay. But to be an inverse image is just look at all the points that get mapped into U. So if you look at this thing, it does. If you look at this thing, it does as well. Okay? Any questions about what the inverse image is? So, what does it mean for a function to be continuous? Well, I claim it's equivalent to saying the inverse image of any open set is open. Take any open set over here, its inverse image will be open over here. And if that's true for every open set, the function is continuous. Okay, let's do some examples so you at least find this result believable, and then we'll try to prove it. So let's look at this example. Here's a function. This is function from R to R, if you like. So let's see. I don't know. Give me some open set in the codomain in Y, if Y here is R. What's an open set look like in the real numbers? Well, it's intervals, open intervals, and unions of things, of open intervals, right? OK. Well, here's one. How about this one? What is the inverse image of this set? I'll call this set U1. What's its inverse image? Well, it's a set of all points that get mapped into U1, right? And what are those points? Well, I can figure that out by just seeing what gets mapped in there. And what gets mapped in there? Looks to me like this interval and this interval. And wouldn't you agree that this set together with this set is open? This is the inverse image of U1. It consists of these two sets. Are you with me? Everybody happy with that? And you see that it does not contain its endpoints because these don't. Yes? OK, let's do another example. What about this open set? I'll call this set U2. What's its inverse image? Help? What does it look like? Natty? Yeah, notice that there's no points that actually get mapped up here, but there are some points that get mapped into this region. And where does it live? It looks like right here. And those, is this set open? Is it? Indeed it is, right? OK. A little bit of a surprise, perhaps. Huh, interesting. Any open set, its inverse image is open if this function is continuous. What would go wrong if the function were not continuous? What would go wrong if the function were not continuous? Let's do an example just to convince you that something funny happens. Suppose I have this function. Can you show me with this function an open set in Y whose inverse image is not open in X? Give me some open set. Yes, Rosalie? Oh, take any open set that's around the closed dot and perhaps does not go all the way, does not include the open dot here, right? OK, good. What's its inverse image? What's the set of all points that get mapped inside? Ooh, it looks like this. And what you see here is this is not open. This is the inverse image of U, if this is U, but this is not open. So because we found one set whose inverse image is not open, this function is not continuous. Good with that? OK, great. All right. Some of you, I think, are thinking a couple of steps ahead, and you're wondering about this example. Suppose this is a function from e to y, and e is not the whole real line, but just some subset of it. How about just this portion? So maybe the function looks like this. Is this function continuous? Well, we've seen already that this is continuous. The only place you worry about it not being continuous at this point, if you use the epsilon delta definition, or if you use the limit definition. There's only one sequence that converges to this point in the domain. If I call this point P, that's the sequence P, 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 P. And its limit is p, and f of its limit is f of p. What you have is it definitely satisfies the sequence definition of characterization of continuity. Is it the case here that the inverse image of open sets is open? Well, this is where you worry a little bit. You might be worried about this set. How about this? Here's an open set. And what's its inverse image? Just P. Is that a problem? Why not? Fiona? Very good. In this example, the inverse image is this point, but this point is open in E because there is a ball around this point in E, and that the ball only contains this one point. So that point by itself is open in E. Are you with me? So in fact, this definition jibes with these pictures jibe with our definition here as we've defined it. So now let's see why, in fact, this theorem is true. Let's try to prove the theorem. Okay. How are we going to prove this theorem? Well, the proof's actually not very hard. And it's perhaps best done by just drawing pictures. Okay. So let's draw a picture here. Maybe get some intuition. Here's x. Here's y. And let's see, which direction do I want to go first? Maybe I'll assume that the function is continuous. I'll go in the forward direction. And I will prove that the inverse image of any open set is open. Okay, so this is the forward direction. Okay, so I'll remind you what it means for a function to be continuous. What it means to be continuous is no matter which point you're at in the codomain, suppose I take a point P, I look at its image f of P, and I draw an epsilon ball around it. If f is continuous, it means there's a delta ball over here whose image is mapped completely in the epsilon ball. That's what it means from the epsilon definition of continuity. Okay, so we'll be able to use that fact if we need it. Now, what's our goal in this part of the proof? If I assume continuity, I want to show that the inverse image of open sets is what? Open. So what I got to start with is an arbitrary what? Open set where? In Y. Let's start with an arbitrary open set in Y. I have no idea what it looks like, but maybe it's this one. Suppose this is open. Okay. My goal is, in fact, to show that its inverse image, the set of all points that get mapped into U, is also open. Yes? I have no idea what its inverse image looks like, but just for fun, I will just draw it as a couple of blobs. Okay? But who knows whether it's open or not? Well, how do I show a set is open? Yeah, I pick a point inside inside the inverse image. So let's call this f inverse of U. I will pick a point in here. Thank you. Now what? Well, what would you like to call it? How about, well, I don't know, x. What do I do with this point x? I want to show that x is a interior point. What does it mean to be an interior point of this set, the inverse image set? There's a ball around it whose images lie completely within U. But why is that? Why is there a tiny little ball around here whose image lies completely within the set U? Because f is continuous, so help me see why, Keiko. What's that have to do with it? Okay, why? Why is there a ball around f of x? Because u is open. Ah, good. U is open, so that makes this thing interior, yes? And that's some ball of some radius epsilon. And now, because of continuity, good, there's a delta around x here, some delta ball. Okay, and what's true about this delta ball? Yeah, its image blob, whatever it is, lies completely in the epsilon ball. But if it lies completely in the epsilon ball, then it lies completely within in U. So, and that's exactly what it means to be in the inverse image of U, is its image lies in U. So let's write down the picture that we've just drawn. So it's not hard to see what happens now. So the proof begins like this. Consider x in the inverse image of U. So maybe I should start here. Given U open in Y, get this out of the way here. Consider some point x that's in the inverse image of U. We'll show x is interior is an interior point of f inverse of U. That's our strategy. And so how did we do that? Well, we said, let's notice that f of p is in U, which is open. So there exists a ball. And it's a neighborhood. There exists a neighborhood n sub epsilon around f of p. And what's true about this ball? It contains f of p, and it's completely within U. Okay? Oh, okay. But then by continuity, so for this particular epsilon, by continuity of f, there exists a delta ball. I'll call it n sub delta around p, such that what? Well, I'll just say this in words, that maps into the epsilon ball, n epsilon f of p. Okay? Maps completely, this is what it means to be continuous. It maps completely inside here. Okay. But then what? Let's see. We've gotten this far, maps completely in here. Oh, but that's within U. So that's within U. So then, so this means what? Well, that means this ball is in the inverse image. So this means this ball, n sub delta of p, lies inside the inverse image of U. And that's, in fact, what we wanted to show. So x is interior. Ooh, I changed my letters from p to x somehow without realizing it. And the easiest thing here is to change. Well, I'll just change this. So this, I meant f of x. Is this the first place I used p? F of x, f of x, f of x, f of x, and f of x. Sorry about that. But this means x is interior. So x is interior. Point of f inverse of U. Nice. Okay. Okay, how about the reverse direction? For the reverse direction, I want to assume that inverse images of open sets are open. And I want to show that, in fact, what? The function is continuous. And I'll use the epsilon delta definition. So how do I do that? Well, let's just start by fixing some p. I don't care which one, because this is going to be a general argument no matter what point p I pick. And I'll pick some epsilon bigger than 0. And so to show continuity, I want to show that for every epsilon, there's a delta, blah, 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 right? So my job is to find a delta. That's our goal. Now, you're going to use, hopefully, this idea inverse images of open sets are open is going to be useful to us. How? So let's see if I'll draw a picture again. X, Y, I'll fix a point P. And now, just like before, I'll start off over here by looking at f of P and taking an epsilon ball. Okay. My job is to find a delta ball here, such that the delta ball maps completely in this epsilon ball. What will I do? By the way, I know the inverse image of open sets is open. What will I do? I know the inverse image of open sets is open. Do you see an open set here that I can use that fact on? Oh, the epsilon ball. Oh, yeah, this epsilon ball is an open set. So its inverse image, whatever it is, and I don't know what it looks like, but it could be really strange. If you don't mind, I'll call this ball B instead of the neighborhood definition. Here's the inverse image of B. It's open. Great. So why does that mean there's a delta ball that maps completely in that epsilon ball? The inverse image of B is open, by the way. And X lives where? It lives at where? I can't hear you. In the inverse image of B. X lies in the inverse image of B. Sorry, X, P, excuse me, P. Sorry, I keep switching between X and P. So, what? Why is there a delta ball that maps completely within this ball here? I know that this blob maps onto this ball. P is interior to this open set. So there must be a what around this thing? A ball. And I'll call that radius delta, and that's the delta that I want. Are you with me? Because it's interior. Okay, so this is the argument. Once you've drawn the picture, it's not hard to see what to do. Let's let B be an epsilon ball about f of P. Then P is in the inverse image of B, which is open by continuity. By the assumption. Which assumption? Inverse images of open sets are open. Oh, then P is an interior point. Since P is an interior point, it's an interior point of f inverse of B. There exists some ball. What ball? Some ball n sub d delta around P that lies completely within the inverse image of B. But then this is the delta that we want. This delta has the required property. Why does it have the required property? It's certainly true that if you're within this delta ball, then the image lies in the epsilon ball. Why? Because this delta ball is in the inverse image of B. Since what? this fact means that f of this ball lies completely within B, which is exactly what it means. So f is continuous. Okay, that's the end of our argument. Natty?
One question.
Yeah.
So you make an epsilon ball in Y. What if some of those points in the epsilon ball aren't mapped to
There's no worry. Whatever this inverse image is, it's some blob, and there may be some stuff here that has no preimage. That's fine. It's kind of like this picture. There's stuff here that has no preimage. It doesn't matter. Okay. In fact, this ball, if we happen to pick it around, well, we're always verifying whether this function is continuous at some p. So we're going to be looking at some f of p. So at the very least, this dot is going to live in, is going to have a preimage. But we don't know necessarily anything around it has a preimage. Because it could be the case that this entire crud actually gets mapped to one point. That's fine. But then what's an open set around this look like? Well, it'll be a ball, but the only thing it'll have in its preimage is all this blob, which is still fine. Okay? Yeah, excellent question. So everything works out. And now I want to show you why this characterization is actually very, very useful. It is surprisingly useful. So let me talk about some consequences here. There are lots of cool consequences of this fact. So here's one. Here's a theorem. Your book actually proves this using the epsilon delta definition, but we can prove it a different way. Suppose I have a function from x to y, I'll call it f, and another function from y to z, I'll call it g. And suppose f and g are continuous. What do you think I can conclude? Take a wild guess. Their composition is continuous. I claim g composed with f is continuous. Okay. Proof. Now, if you want, you can do this using the epsilon delta definition, but it's messier than it needs to be. Let's think in terms of the open set characterization. If I want to show that this composition is continuous, that's this composition, G composed with F, do F first, then G. All I have to do is show that the inverse image of an open set in Z is open. So Kevin, help me out. How do I show the inverse image of an open set here is open over here? Good, and that's the inverse image of the composition. Done, right? Beautiful. If you used epsilons and deltas, you'd have to be a little more, you'd be a little bit more of a mess. Okay? So the way to do this is given U open in Z, G inverse of U is open in Y. By what are we saying? G's is continuous, right? That's really what we're using, right? But then F inverse of G inverse of U is open in X because F is continuous. But then this thing is just the inverse of G composed with F. And that's enough, right? Beautiful, beautiful idea. Let me mention another consequence, which is sometimes useful to keep in mind. If the inverse image of open sets is open, what do you think the inverse image of closed sets is? Closed. Why? by taking complements. So f from x to y is continuous if and only if for all closed k in y, f inverse of k is closed in x. Another useful characterization of continuity. And the proof idea, I won't write out the whole proof, but the idea is this simple idea. If I take the inverse image of k and the inverse image of k complement, what do you think the relationship is? That's the set of all things that are mapped into k and the set of all things that are mapped into k complement. Could they contain anything in common? No, so they're disjoint. Do they contain everything? Yes, they do. So in fact, this is the complement of the inverse image of the complement. And so if you use this idea, and you know that k is closed and k complement is open, then the inverse image of an open set is open, and the complement of that is closed. Done. Okay? Very nice. That's another consequence. Here's another consequence. Oh, this one's a good one. I like this one. Continuous functions have the curious property that they preserve. We saw that they preserved limits. They also preserve compactness. So here's a theorem. Suppose I have a function from x to y that's continuous, and x is compact. I claim this means that the image of x is in fact compact. In other words, if the space is small in some sense, remember compact kind of means it's small, it's the next best thing to being finite, then its image can't be too big, is really what it's saying. Right? Oh, interesting. Let's give a proof. This is a very nice proof, actually. Here's a space, X. Okay? And here it's getting mapped into some space Y. Right? So here's a space. This point here gets mapped over here. This one here gets mapped over here. This here gets mapped over here. Right? Okay. And this here gets mapped over here. And maybe this whole thing, whatever it is, gets mapped to just a subset, right? So it's not necessarily the whole thing. With me? Okay. Good. I claim that this image, whatever it is, I claim that it's open. Excuse me, not open. It's compact if x is compact. That this thing is compact. So how do you show that a set is compact? Take a cover of this creature and show that it has a finite subcover. Good. Let's take a cover. Let's cover it with these blue sets. There. Imagine there's possibly infinitely many of these blue sets. Here's a cover. Okay? I'm going to call the cover sets the V's. Now what? Remember, the function's continuous. So what's really useful here is the open set characterization. What can I say? Rosalie? Ah, yes. In fact, you'll get a bunch of sets over here, etc. Good. If you don't mind, I'm going to call these inverse images the U sub alphas. I'll let them be the inverse image of the V sub alphas. Good. Help. Now what? Fiona. Ah, finitely many cover. Good. So we're piecing together a proof here. So proof starts here. Cover, let's let V alpha be a cover of f of x. Good. that's step one. Step two is let's let U be the inverse images of the V alphas. Step three is to notice that finitely many, by compactness, sorry, what did you suggest, Fiona? What should I do? Good. By compactness of X, there exists a finite subcover, which, if you don't mind, I'll call U1 through UN. Good. Then what? Finally, many of these blue things cover. Therefore, the corresponding V's cover Y. Then V1 through Vn cover f of x. Why? Well, that's just what it means, right? The inverse image covers this, then all the points are in some inverse image. Therefore, f of that point is in V alpha, right? If x is in U alpha, then x is the inverse image of some point. So f of x is in V alpha. Okay. Perfect. That's great. So this should be somewhat surprising to you. You have a compact set, and its image can never be, has to be compact. This means that if you have a function from the line into itself, suppose I take a subset, is there a way to map an interval onto the line, onto the whole line? Yes, there is a way to do that. You could take this interval and stretch it out so that it goes off to infinity. Okay. E to the x would take. Have to be a little more careful. But for instance, between 0, well, you have to be a little more careful, but there's a way to do it, right? Okay? But wait, what this means, it's not possible to map a closed interval onto the entire real line. It's not possible if f is continuous for continuous f. That's impossible, because the endpoints have to go somewhere, basically, right? Interesting. Let me finish with a couple of other consequences that follow from this useful fact. Inverse image of open sets is open. Has lots of profound consequences. Here's a corollary of the previous result. If you have a function from a compact space X into Rk, then the image has to be closed and bounded. Why? Well, the image has to be compact, and in Rk, by the Heine-Borel theorem, it has to be closed and bounded. Good. Well, that's what this means then. Check this out. Suppose I have a function from x into R, x compact. Well, then f achieves its maximum and minimum. Give me a compact set, map it into the real numbers. Think like a temperature function. Then there's a point, maybe this is a disk. There's a point on the disk that achieves the maximum and the minimum. You use this fact all the time in single and multivariable calculus when you're doing minimization problem, right? You could think, for instance, an interval. You could think, for instance, a disk. It has to achieve its maximum and minimum. Why? Well, its image has to be closed and its image has to be bounded. The image being bounded means it has a supremum and an infimum. Being closed, it means that it must contain its supremum and its supremum. Done. Right? Amazing fact. It's not a mean value theorem. It's more of a maximum maximum principal, right? Okay, here's one final fact, which we'll finish with, which is kind of a nice theorem. Suppose you have a map between x and y that's a bijection, which means there's one-to-one and onto, and it's continuous. And let's suppose further that x is compact. Now, when you have a bijection, so you've got a one-to-one correspondence here, then you can talk about the inverse function because every point has an inverse, a unique inverse. And you might worry, if you know the forward direction is continuous, is it true the backwards direction is necessarily continuous? The answer is no, not necessarily. But if x is compact, then the forward direction being continuous implies, in fact, that the backwards direction is continuous too, which is kind of an amazing fact. And has a very, very simple proof. So let's just do the proof, which will take 1 minute. So the proof is very simple. To show inverse image is continuous for an inverse function, you're really trying to show, if you take an open set here, then the inverse of the inverse, which is going forward, that's open here, right? That's the inverse image of the inverse function is going forwards. So I'll start with a set open. Suppose U is open in X. Well, guess what? That means that U complement is closed. Well, that wasn't so bad. But now the complement is closed. I can use a closed set characterization. It's closed in a compact set X, so U complement is compact. But if U complement is compact, then its image is compact. And if its image is compact, then it has to be closed. Is closed. So, in fact, f of u is open, which is enough to show that the inverse function is continuous. So a function that's bicontinuous, a bijection, and bicontinuous is sometimes called a homeomorphism. What it means is that these things are topologically equivalent. OK, that's a great place to stop. And next time what we'll do is we'll talk about uniform continuity. OK.